Hello everyone, welcome to Get Wallah. So if everything is fine, comment in comment box. If video is clear, audio is clear, please thumbs up. Okay. So we'll be doing 10 questions of EDC today, and these questions are framed question through which I will be covering diode, I will be covering semiconductor physics, I will be covering MOSFET, I will be covering PJT. So through these 10 questions, I will revise your concepts which are very important in upcoming GATE 2023 examination. So first of all, please comment whether video and audio everything is clear. So we'll start with the first question. Then we'll start with the first question, okay? And whatever you are going to learn today, it will definitely going to benefit you in the upcoming GATE examination 2023. Okay? Okay? Yes, Nachiket. Yes. Hello, है ना? So shall we start from the first question? If everything is clear, we can start with the first question. And this question is from semiconductor physics and very beautifully framed. And you are going to learn from all these 10 questions. And this series will continue. And we will be covering 10 questions of every subject. And through those questions, we will be covering your important concept which can be very useful in upcoming 2023 examination. Okay, so shall we start? Thumbs up if we can start, hai na? Chalo. So we'll start with this first question, very beautifully framed question of semiconductor physics. And sometime when you just read the concept and practice a lot of questions but not your concepts are not very crystal clear, then these questions can be very dangerous in GATE examination, hai na? And you can find out the wrong answer, and wrong answer will definitely be there in the option. Okay, so we'll be doing this first question. Everybody will try, and then we'll discuss what the question is. Okay, so answer, try to solve it and then answer. Okay, good afternoon, good evening, good afternoon. Okay, so this is the first question. Everybody will try and then try to answer. You can find the answer, then it's totally fine. If you won't, I will discuss the solution definitely. Okay, so there is no problem. The most important thing, you should try. If you are not trying, then you are not learning. As simple as that. Okay, anybody got the answer? Anybody? Now I will discuss the solution. Okay, so there are questions from diode, there are questions from MOSFET, BJT, semiconductor physics. This question belongs to semiconductor physics. Okay, A and B, sir. Herculean is saying A and B, sir. How is this possible? At the same time, semiconductor can't be N type and can't be P type. This is totally wrong concept. Okay, so it's not possible, Herculean. At the same time, a semiconductor could be N type as well as could be B type. Not possible at all. Either it will be N type or P type or intrinsic type. Okay, so it's not possible a semiconductor will be N type as well as P type. It's totally wrong concept. If you are saying A and B, then your concepts are not good about semiconductor physics or semiconductors. Okay, so let me discuss the solution. Okay, in a germanium crystal, we experimentally found that. We did an experiment and then we experimentally found these datas. Hole concentration, net hole concentration. Concentration of hole means net hole concentration. Net hole concentration is what? P naught is equals to, given as 5 into 10 to the power 5 per centimeter cube. Okay, and then what we find? Experimentally we found that the acceptor concentration That's why this question is very, very beautiful question. And 1.25 into 10 to the power 15. जो आप प्रैक्टिस करते है ना, ठीक है. 1.25 into 10 to the power 15 per centimeter cube. Intrinsic carrier concentration is also given. Ni is also given 2.5 into 10 to the power 10 per centimeter cube. We found these datas. Maybe another data is available, but we experimentally didn't found. Yeah, that is not mentioned in the question. This might be possible. Okay, and experimentally, whatever data we found, some of the data which are experimentally found are given as hole concentration, acceptor concentration, and intrinsic carrier concentration. So always remember, the net electron or net hole concentration will decide which type of semiconductor is this. Here hole concentration is given. If hole concentration is less than Ni, then semiconductor is definitely of N type. Because in N type semiconductor, hole concentration, net hole concentration is less than intrinsic carrier concentration, and net electron concentration is greater than intrinsic carrier concentration. Similarly, if there is a N-type semiconductor, if there is a P-type semiconductor, then electrons concentration N will be less than Ni, N naught will be less than Ni, and P naught will be greater than Ni, holes concentration. So here clearly holes concentration is mentioned. है ना? Holes concentration P naught is clearly less than Ni, so semiconductor is N-type. So whatever option is of P-type is totally wrong. B and D could not be the option. 100% could not be option. And according to mass action law, N naught into P naught is equal to Ni square. Whatever N naught concentration is 2.5 square, square 10 to the power 20 upon this come out to be 1.25 into 10 to the power what? 15 per centimeter cube. This is the concentration of net concentration of electrons. This is the net concentration of holes. Since electrons concentration is greater than Ni and holes concentration is less than Ni, then semiconductor is definitely of N type. And which option is correct? Which option is correct? The C option is correct. And definitely this semiconductor is doped with N-type impurity as well as P-type, where P-type impurity concentration is given. This is impurity concentration. Is there said, is anything is mentioned that only acceptor concentrations are there? If only acceptors are added in a semiconductor, then definitely the semiconductor will be P-type. If only acceptors are added. If only donors are added, then semiconductor will definitely have N-type. But if both are added, acceptor and donor both are added, then semiconductor could be of N type. If Nd is greater than Na, semiconductor could be P type if Na is greater than Nd. So here, and in mass action law, there is N naught is concentration of electrons, not Nd. P naught is concentration of net concentration of holes, not Na. Remember that, hai na? So here actually donors are also there. And effective donor concentration is approximately equal to electrons concentration, because this semiconductor is of N type. So Nd dash effective donor concentration is 1.25 into 10 to the power 15. And total donors are what? Because 1.25 into 10 to the power 15 donors are also there, which will be used in compensation of this Na acceptors. So actually this is effective donor concentration, and effective donor concentration is what? Net donor concentration minus net acceptor concentration. So actually total donor concentration Nd is nothing but effective plus acceptor, and that comes out to be 2.5 into 10 to the power 15. Actually this semiconductor is doped with this much of acceptors and this much of donors. So effectively this much of donors remains, and they made this semiconductor is of N type with holes concentration is equal to 5 into 10 to the power 5 and electrons concentration is equal to 1.25 into 10 to the power 15, approximately equal to the effective donor concentration. So that's why the option is C option is correct. And this question is why very beautifully friend, because many of you found that the acceptor concentration is 1.25 into 10 to the power 15. So this is a p type and holes concentration is equal to 1.25 into 10 to the power 15. Holes concentration is mentioned here. Is because this data is hidden. This you have to think with your common sense, with your logics. So holes and electrons concentration decide which type of semiconductor. If holes concentration is less than Ni, definitely N type, because in N type holes concentration are less than Ni and electrons concentration are greater than Ni. In P type holes concentration are greater than Ni and electrons concentration are less than Ni, and in intrinsic semiconductor holes and electrons concentration are equal to intrinsic carrier concentration. Now clear? Everybody clear? So this question is, that's why this is a very beautiful question, because this 1.25 into 10 to the power 15 is the electron concentration. This beautiful, hai na? Data are so chosen so carefully, the holes and electron concentration that you think acceptor concentration B and C. चलो नेक्स्ट क्वेश्चन पे आ जाते हैं. चलिए सॉल्व करिए. ट्राई टू सॉल्व इट एंड आंसर. ओके, थोड़ा बहुत मैं हिंदी भी अगर बोल दूंगा एक आध सब तो समझ जाना, इतना कोई टेंशन वाली बात नहीं. मैक्सिमम चीजें हम इंग्लिश में डिस्कस करेंगे, ठीक है. ओके, तो ट्राई टू सॉल्व दिस क्वेश्चन. दिस इज क्वेश्चन ऑफ ऑप्टिकल इल्यूमिनेशन. So everybody got the question, first question. So always try to decide the type of semiconductor on the basis of net electrons concentration and net holes concentration. It might be possible that semiconductor is doped with N-type as well as P-type impurities at the same time. Then depending upon which impurity concentration is higher, the semiconductor could be of N-type, could be of P-type. Okay? Clear? Try to solve this question, okay? So hopefully you got something from this question. If you are saying that semiconductor is P-type, then definitely P are majority charge carriers. Cannot say that semiconductor is P-type and holes are in minority. You can't say like that, okay? So try to solve this question. This is case of illuminating a semiconductor at one of the end. It's a very simple question, but many of you can solve it wrongly by using the wrong formula. That's why this question is there. Try to solve it. Try to solve it. Okay. Anybody got the answer? All 10 questions are framed beautifully. So you will be going to learn something which will benefit you in the GATE upcoming examination 2023. Herculean, are you clear with the first question? Herculean. Anybody got the answer of this question? Anybody? Anybody? Try to solve it. Try to solve it. Okay. Okay. So let me try to solve it. You can see the solution. Okay. So this is N-type semiconductor. Whenever there is case of optical illumination, you always do first thing. You always do first thing that try to find out the concentration of electrons and holes before optical illumination. Okay, before optical illumination. So before optical illumination, it is N-type semiconductor because donor type doping Nd is there. So electrons concentration N naught, that is called as thermal equilibrium concentration before optical illumination, is approximately equal to Nd and approximately equal to 10 to the power 14. And at thermal equilibrium, I can use the mass action law. When optical illumination will be there, you cannot use the mass action law. You can use the mass action law only at thermal equilibrium when there is no optical illumination at all. So there is P naught is equal to Ni square upon N naught, yeah, Nd, Ni square Ni is given. Ni is given. Yes. Ni is given 1.5 into 10 to the power 10. So 2.5 into 10 to the power 20 upon 10 to the power 14 is 2.25 into 10 to the power 6 per centimeter cube. What I am going to make you learn from this question is very, very important. Listen very, very carefully. I know that many of you have solved this type of question, and just remember one formula, and by using that formula you solve all the question, you find the answer, and therefore you assume that this is absolutely correct and I will always do this formula and I will always find the correct answer. But if there is problem with that formula, if there is any approximation with that formula and you don't know, then gate examination can make you solve the wrong solution. So that's why this question is there. Okay, chalo, let me try to solve it. When light falls at the one side of the semiconductor, then obviously excess minority and excess majority charge carriers will be generated at this end, at x is equal to 0. And in steady state, at x is equal to 0, the minority charge carrier concentration, what are the minority charge carrier concentration? Holes are the minority. Excess minority charge carrier concentration at x is equal to 0. At x is equal to 0, at x is equal to 0 will be, at x is equal to 0 will be GOP into the minority carrier lifetime. GOP is optical generation rate into tau p, which is given as what? 15 nanosecond, and this is given as 1.5 into 10 to the power 17. So 1.5 into 10 to the power 17 into 15 nanosecond will be converted into second, because this GOP is given as 1.5 into 10 to the power 17 per centimeter cube per second. Okay, so this comes out to be 22.5 into 10 to the power 17 9 8 है ना 8, or you can say that 2.25 into 10 to the power क्या 9 per centimeter cube. These many excess holes are generated due to optical illumination or due to light at x is equal to 0. So the excess minority carrier concentration increases at x is equal to 0, and on other side of the semiconductor there are the low concentration of holes, that is equal to 2.25 into 10 to the power 6. And here the concentration of holes, excess holes are generated due to this. Total concentration of holes at x is equal to 0 increased above this equilibrium value. Here P naught holes are already there. At x is equal to 0, P naught holes are already there due to thermal generation. But additionally, this much of holes added in excess at x is equal to 0 due to optical illumination. So total hole concentration at x is equal to 0 is what? P naught thermal equilibrium plus excess, that is delta P. So holes concentration is here P naught plus delta P, while in other part of the semiconductor hole concentration is P naught. So concentration of holes is higher at x is equal to 0 compared to the other portion of the semiconductor. So holes will flow from higher concentration to lower concentration, and a diffusion current will flow. But as soon as hole will move from left to right, they will encounter with the electrons of n-type semiconductor and they will recombine. And as they will recombine, their concentration falls. So excess minority carrier concentration which are generated at x is equal to 0 due to optical light, when they flow inside the semiconductor, their concentration falls from this x is equal to 0 value. And they falls exponentially. They follow the exponential profile. So the concentration of excess holes, the concentration of excess holes are generated at x is equal to 0 in which concentration? 2.25 into 10 to the power 9. And these excess concentration will fall as holes will move from x is equal to 0 to x is equal to 200 micrometer or x is equal to L. So these holes concentration, excess hole concentration will fall exponentially, because a differential equation is formed, and that is first order differential equation, and solution is of exponential nature. So these excess hole concentration fall exponentially x upon LP, e की power minus x upon LP, where LP is the diffusion length, because due to diffusion the charge carrier concentration decreases, and negative power because exponentially they are decreasing. So excess minority carrier concentration falls as we move away from x is equal to 0. So total hole concentration at x is equal to x will be Px is equal to, at every point from x is equal to 0 to x is equal to 200 meter, thermal equilibrium concentration of holes is P naught. Thermal equilibrium concentration of holes is P naught at every point from x is equal to 0 to x is equal to L, या x is equal to 0 to x is equal to 200 micrometer. And excess hole concentration at x is equal to 0 is this, and as we move from away from 0, excess hole concentration falls exponentially. So total concentration will be thermal equilibrium plus at any point x the excess hole concentration. So total concentration at any point x is equal to thermal equilibrium plus this. This is the formula of minority carrier concentration. Many of you directly use this formula only, delta P e की power minus x upon LP, and that's where you falls into the trap of gate examination. Okay, so this is the exact formula. Whenever this quantity will be very high compared to this, we can neglect this. At, let's for example, at x is equal to 0, Px will be P naught plus delta P. P naught thermal equilibrium and delta P due to, and this P naught is, delta P is 2.25 into 10 to the power 9, while P naught is 2.25 into 10 to the power 6. This is 10 to the power 3 times higher than the P naught at x is equal to 0. 1000 times is higher. Delta P is 1000 times higher than P naught. So at x is equal to 0, I can neglect this P naught value. But as we move away from x is equal to 0, this whole quantity falls below this point. And then this P naught and this whole quantity will be comparable, and therefore I will not be able to neglect this P naught compared to this value. And that's where this question is. Okay, so what is saying? At x is equal to a, the concentration of minority क्या है? Thermal generation, the concentration, total hole concentration or minority carrier concentration, that are from thermal generation as well as from optical. You cannot only take the optical generation concentration. They are the excess minority carrier concentration. And when thermal generation concentration will be added, then only you will be getting the overall minority carrier concentration. And here concentration of minority carriers are asked, not excess minority carriers. These are the excess minority carriers. These are the profile of excess minority. Delta P is excess minority, and this profile, exponential profile, is of excess minority, not total minority. Remember that. So A, value is A when x is equal to what? When x is equal to, value is A when x is equal to what? 5 micrometer, है नहीं 7.5 micrometer. X at is equal to 7.5. Put that value P naught plus delta P e to the power minus x upon LP. X is 7.5 and LP is 5 micrometer. Okay, LP is 5 micrometer, so 7.5 upon 5, 1.5 aa jaye. Okay, so this is the first. B is what? At x is equal to 30 micrometer. Okay, here also you cannot neglect delta P e की power minus x e की power minus 1.5. You cannot neglect P naught with respect to this value. Everybody is just using this formula and find the wrong answer. P naught plus delta P into e की power minus 30 upon what? 5. So that is e की power minus 6. Okay, so find the, if this P naught can be neglected, you can neglect it. If this is comparable with this value, you cannot neglect it. So find the total value of A, then find the total value of B, then only you will be finding the right answer of A by B. If you are just using this formula, you will be finding the wrong answer, because here P naught cannot be neglected with compared to delta P e की power minus 1.5, because these two values will be comparable, and delta P e की power minus 6 will be very small value. So with respect to this value, you cannot neglect P naught. So you have to find the right answer by using the exact values. Whatever answer will come, use this right formula. So in many questions that is asked in gate examination, that is already asked in gate examination, this value comes out to be very, very high in many cases, and that's where you neglect this P naught. And that's where you learn that only by using this formula I can find the right answer. And that's where your concepts are becoming wrong, and you will be in trap whenever the values will be comparable. Whatever answer is, try to solve it and just put it in the comment box. Okay, so we'll be moving to the next question. Okay, so this is the misconception. Always remember, thermal equilibrium concentration will always be added. If that value can be neglected, you can neglect it. If that value is not neglected, then you cannot neglect it. Okay, so try to solve this question. Try to solve this question. It belongs to Fermi level, and a very beautifully framed question of Fermi level, where your concept clarity should be very, very good to solve this question. Okay, so have you learned something from these two questions? Please comment in the comment box. Have you learned something? All the questions which are there in this session will make you learn something for sure. The misconception which you carry with your brain in the examination will definitely be removed from these 10 questions. Okay, so approximation you should remember when they are valid. When they are valid, if you are remembering any approximate formula, then always remember when that approximation is valid. If approximation is valid, you can use that formula. If approximation is not valid, you cannot use that formula. So if you are solving that question by that approximate formula and approximation is not valid, you will always be getting the wrong answer. Okay, so try to solve this question, and then we'll learn something out of this question. Okay, try to solve it. Everybody, whoever is in this session, try to solve it. Okay, सॉल्व करिए जल्दी से. बताइए. चलिए मैं सॉल्व करता हूं. ठीक है, I will make you learn something. In a semiconductor, Fermi level is 0.2 electron volt below the conduction band energy level EC. We want to change the position of Fermi level to 0.35 electron volt below conduction band energy level EC. Then impurity and its concentration will be given. EZ is equal to, EZ is energy gap EC minus EV, 1.1 electron volt. Ni is given, thermal voltage is given. So firstly, I will draw the energy level diagram in first case. Okay, so this is the energy gap EC minus EV, that is given, and that is nothing but equal to what? 1.1 electron volt. So this mid of the band gap, which is also called as intrinsic Fermi level, will be what? 0.55 electron volt, and this is also 0.55 electron volt, because this point is midpoint. So this is 0.55 plus 0.55, total is 1.1. Okay, so this is EC basically, and this is EV. Okay, now the Fermi level in first case initially is 0.2 electron volt below this conduction band energy level EC. So Fermi level is where? This EF is where? This is nothing but 0.2 electron volt, 0.2 electron volt below the conduction band energy level. Okay, now from seeing this Fermi level diagram, what you can conclude? You can conclude that as the Fermi level lies above the intrinsic Fermi level or mid of the band gap, so this semiconductor is definitely of N type. So definitely there will be donor impurity added in the semiconductor. So this Fermi level diagram belongs to n-type semiconductor with doping concentration Nd. Okay. So if I know the formula of shifting, you know, this is the intrinsic Fermi level EI. When there is no impurity added in a semiconductor, Fermi level lies as the mid of the band gap as EI. When you add donor impurity, semiconductor becomes of n-type and Fermi level shift above intrinsic Fermi level, and that shift, this much of shift is there, EI to EF. This shift, which is 0.35 electron volt, definitely na? This total is 0.55, so this shift is 0.35 electron volt. This shift is equal to nothing but EF minus EI, which is there in this case is KT ln Nd upon Ni, where Nd is doping concentration of pentavalent type. So if Nd donors are added, then Fermi level is shifted from EI to EF, and that shift is equal to 0.35 electron volt, and that is equal to KT ln Nd upon Ni. Okay. So definitely KT is given, Ni is given. I can find out the value of Nd here. KT is nothing but 0.025 volt. So KT is nothing but 0.025 electron volt. So 0.35 upon 0.025 is equal to ln Nd upon Ni. So initially, how many donors are there per centimeter cube? I can find out by this shift formula from the initial Fermi level diagram. Okay. So Nd will come out to be Ni into e to the power 0.35 divided by 0.025. Okay. So this is nothing but 350 upon 25. So it will come out to be Ni into e to the power 350 upon 25, that is, e to the power 14. Okay. So Ni into e to the power 14. This much of donors are added in intrinsic semiconductor, and then Fermi level shifted from EI to this EF, and this EF is 0.2 electron volt below the conduction band energy level. Now in this semiconductor, which is already of n type, you want to add a type of impurity such that the Fermi level shifted and new position of the Fermi level is 0.35 electron volt below conduction band. So new Fermi level, you want to add some impurity such that the new Fermi level position is EF dash, and this EF dash is nothing but 0.35 electron volt below the conduction band energy level, or you can say that 0.2 electron volt above the intrinsic Fermi level. So you want to add impurity in which semiconductor? N-type semiconductor, where Fermi level is already at EF. You want to add impurity such that the Fermi level should shift downward and comes to the point at EF dash, which is 0.35 electron volt below the conduction band energy level EC. Okay. So whenever you require a downward shift, you always add trivalent type impurity, and whenever a upward shift is required, you always add pentavalent impurity. For example, let us think, when semiconductor is of pure type and you add pentavalent impurity, Fermi level shift upward, and when semiconductor is of pure type, when you add trivalent impurity, Fermi level shift downward. So whenever downward shift is required, you always add trivalent impurity, and whenever upward shift is required, you always add pentavalent. So phosphorus will not be added. These two options are totally wrong, because whenever you add phosphorus, that is pentavalent impurity, Fermi level will shift upward in upward direction, not downward. Here Fermi level is downward shifted from EF to EF dash. Okay. So now you need to find out how many boron trivalent impurities will be added for shifting downward the Fermi level from EF to EF dash. So new Fermi level EF dash is 0.2 electron volt above the intrinsic Fermi level. So EF dash minus EI. If initially, because shift formula you always know with respect to intrinsic Fermi level. So EF dash minus EI. If my semiconductor is of the nature of intrinsic and I added some donor impurities and try to shift the intrinsic Fermi level from EI to EF dash, then how many donors are required to be added? KT ln ND dash, let's say ND dash donors are required to be added, then ND dash upon NI. Because I know this formula only, because EF dash is above the EI. So obviously there will be net donor concentration. Okay. So ND dash will come out to be what? This is Ni e to the power EF dash minus EI upon KT. EF dash minus EI is 0.2. 200 upon 0.025. That is nothing but e to the power 8. So if I finally want to Fermi level at EF dash, what I want? Finally I want the Fermi level to be at EF dash. So Fermi level to be at EF dash, effectively donor should be ND dash. With respect to intrinsic semiconductor, if I have effective donor concentration equal to ND dash, which is nothing but equal to Ni into e to the power 8, then my Fermi level will be 0.2 electron volt above the intrinsic Fermi level, which is nothing but EF dash. And initially, how many donors are there? Because I am adding the impurity to the N type semiconductor, ND. I want this much effective donor to be remain, so that the Fermi level to be at EF dash. And initially I have this much donor. So I need to add boron or acceptor type impurity, so that apart from ND dash, other donors will be compensated by Na. So how many Na should be added? How many Na should be added? Effectively this much donor should remain. Effectively this much donor should be remain. Okay. So you can say that effective donor concentration should be ND dash. You are getting my point? If effective donor concentration will be ND dash, then Fermi level will be at EF dash with respect to intrinsic Fermi level, and that will be what is my requirement. But already this much of donors are there, so I will add acceptor, so that extra donors apart from ND dash will be compensated by the acceptor impurity. Okay. So effective donor should be ND dash, should remain ND. This much of donors are already there, and I added Na acceptor such that ND minus Na remains only ND dash. So Na will be what? ND minus ND dash. So if you add ND minus ND dash acceptors, then Na acceptor will compensate ND minus ND dash donors out of ND donors, and remaining donors will be if you add ND minus ND dash acceptor, then out of ND donors, ND minus ND dash acceptor will compensate ND minus ND dash donors out of ND donors, and then remaining donors will be ND minus ND dash, which will be equal to ND dash donors. ND dash donor will remain, and this ND dash donor will make this semiconductor N type and Fermi level at EF dash, which is our requirement. So we will be adding ND minus ND dash borons, and answer will be BRD. You can find the answer. Okay. So I am not calculating. Okay. B or D. This much of acceptor you need to add, so that the Fermi level falls from EF to EF dash. Okay. So we will move to the next question. This question is easy question. Okay. But very tricky. Try to solve this question. Okay. Try to solve this question. Everybody try to solve this question. Okay. Try to solve this question. Try to solve this question. So sure. Let me try this question. Okay, you are getting the answer. This is very easy question. You can solve it very quickly. Okay. Always remember the shift formula is valid with respect to intrinsic Fermi level. So always use that formula very carefully and then analyze your concepts. Okay. Fermi level diagram of a doped semiconductor is given below. It is a doped semiconductor obviously because the Fermi level lies above intrinsic Fermi level. So this is a n-type semiconductor and obviously you doped it with the donor type of impurities. Okay. So the Fermi level is at 0.2 electron volt just below the conduction band energy level. To change the position of Fermi level, जैसे अभी किया था वैसा ही है. To change the position of Fermi level to EF dash, which is 0.2 electron volt above the valence band, the new dopant concentration added will be. So now we want the Fermi level to be at EF dash, which is 0.2 electron volt above the valence band. Okay. So obviously, initially my semiconductor is of N type and finally my semiconductor is of P type because Fermi level EF dash is below the intrinsic Fermi level. Okay. So the dopant concentration, only dopant concentration is asked. Now it is not asked which type of dopant should be added. Here also Fermi level, we have to move Fermi level from EF to EF dash, which is downward shift. And always remember, for downward shift I have always I need to add trivalent type of impurities. Okay. So firstly I will find out how many donors are already there so that the semiconductor is of N type and Fermi level is above the intrinsic Fermi level by what? This is total is 0.6 because total energy gap is 1.2, mid of the energy gap is 0.6 electron volt. This is 0.6, so this is 0.2, this is 0.4. Initially my Fermi level is 0.4 electron volt above intrinsic Fermi level. So how many donors will be added in the pure semiconductor? KT ln. Let's say ND donors are added in the intrinsic semiconductor so that the intrinsic Fermi level moves. Fermi level moves from the intrinsic Fermi level to the EF 0.4 electron volt above. So here ND will be EF minus EI is 0.4 electron volt. EF minus EI upon KT, NI EF minus EI is 0.4 electron volt upon KT. This much donors are already present in the semiconductor, which is doped semiconductor, and Fermi level lies at the EF. Now I need to add a impurity so that the Fermi level moves from EF to EF dash, and EF dash position is 0.2 electron volt above the valence band. Now the new position of the Fermi level is below the intrinsic Fermi level, so definitely this is a P type semiconductor, and this position with respect to EI is what? 0.4 electron volt below the intrinsic Fermi level. This is 0.2, this is 0.4. So think like that. If initially my semiconductor is of intrinsic type and I need to move the Fermi level from EI to EF dash, that is 0.4 electron volt below the intrinsic Fermi level, then I need to add acceptor in pure semiconductor, and that acceptor concentration Na will be what? The shift is from EI to EF dash. If intrinsic, initially my semiconductor is of intrinsic type and I need to move the Fermi level from EI to EF dash, that is 0.4 electron volt below, then I need to add Na acceptor atoms in pure semiconductor which is intrinsic type. Then Fermi level will shift from EI to EF dash, and this Na will be what? This Na will be Ni e to the power 0.4, because EI minus EF dash, this shift is downward shift. EI minus EF dash is 0.4 electron volt divided by Ni. So if already semiconductor is of pure type, then only I will add this much of acceptor, then Fermi level will shift from EI to this. But my semiconductor is initially of N type and Fermi level is at this position. So already this much of donors are there. So I need to add acceptor so that they compensate donors, initial donors, so that the semiconductor becomes from n type to intrinsic type. Then I can add additionally this much of donors so that the Fermi level will shift from EI to EF dash. So first I need to add acceptor which will compensate donors, initial donors. So how many donors I need to add? Initially, how many acceptor I need to add to compensate initial donors which are there due to n-type semiconductor? I need to add Na dash acceptors which will be equal to in number with Nd. So I need to add Na dash acceptor which will be equal to the initial donors. Then this Na dash will compensate all donors and semiconductor will be converted into intrinsic type and Fermi level will shift from EF to EI. Now I will add this much of acceptor additionally to shift this intrinsic Fermi level to this. So total acceptors are added are Na double dash is equal to Na for shifting intrinsic Fermi level to EF dash and Na dash for shifting EF to EI. So total will be Na dash. And this is Na plus Na dash is equal to Nd. And if you look at very carefully, the magnitude of Nd and magnitude of Na is same. Ni e to the power 0.4 upon Ni. Ni into e to the power 0.4 upon Kt. 0.4 upon Kt. This is 0.4 upon Kt. Okay. 0.4 upon Kt. So this is nothing but equal to 2 Nd. So I need to add 2 times the initial doping concentration, 2 times the concentration of acceptor added is nothing but 2 times the initial dopant concentration. Nd is the initial dopant concentration which is already present in the semiconductor due to which the semiconductor is of n type. So I need to add 2 times Nd concentration of acceptor to convert the semiconductor from n type to p type and to shift the Fermi level from EF to EF dash. So answer is double of the initial dopant concentration. Okay. So next question. This is the easy question. Try to solve it. Okay. Try to solve it. This is of the easy one. This is of the easy one. Okay. Try to solve it. Try to solve it. अच्छो चलिए जल्दी से सॉल्व करिए इसको. जल्दी से सॉल्व करिए. बताइए इसका आंसर. Two identically doped PN junction has doping concentration Na and Nd respectively on P side and N side. Doping concentration of two PN junction diodes are same. Under reverse bias condition, both are under reverse bias condition. How much reverse bias is applied, that is not given. The magnitude of the reverse bias voltage applied at PN junction 1 and PN junction 2 is not mentioned. Okay. Variation of electric field is given inside depletion region of two diodes, because in reverse bias condition diode will be in there will be depletion region across the junction, and as reverse bias increases, depletion region width increases on both the sides, P side as well as on N side. Okay. So always remember, in the depletion region, electric field varies linearly if the doping concentration is uniform. So there is, from this electric field diagram, I can say that as electric field varies linearly inside depletion region, therefore P region is uniformly doped as well as N region is uniformly doped. Okay. If non-uniformly doped if P region or N region is non-uniformly doped, then electric field will vary linearly with distance, non-linearly with distance. If electric field is varying linearly with x, then definitely the semiconductors P or N regions are uniformly doped. So here P and N regions are uniformly doped. In N region of the depletion, on N side of the depletion region, the slope of the electric field is positive, and in P region, the slope is negative. So from this diagram, I can say that this is the junction, and this is N side, and this is P side. This is P side, and this is N side. Why? Because here slope is positive. This is negative slope. This is negative slope. This is positive slope. Okay. Now I need to find out this magnitude E1 and E2, and E1 and E2 are negative. You can say that this is the maximum electric field. Why E1 and E2 are negative? Because the direction of the electric field inside the depletion is always from N to P region, is always from N to P region. So electric field is from N to P region, that is in the negative x direction. This is N and this is P, that is negative x direction, and if the electric field is in negative x direction, then it is negative, and if it is in positive x direction, then it is said to be positive. That's why this electric field is plotted below the x axis. That's why this is negative electric field, because of its direction. Okay. Now this slope on N side, the slope of the positive slope is nothing but always equal to Q upon epsilon into doping concentration on N side. Since N side of the region is, in case of both the diodes, is uniformly doped, yeah, identically doped, so slope of Q upon epsilon into Nd. Here also the slope of electric field is Q upon epsilon into doping concentration on N side. Here also the slope of the electric field on N side is Q upon epsilon into the doping on N side. As doping on N side is Nd in both the cases, so slope is Q upon epsilon into Nd, obviously. Now I need to find out this E2 or E1, magnitude of E2 or E1. So by seeing this 1 and 2, you can always say that this E2 is magnitude is greater than this E1. You can always say. But if you want to find out, then I can find out. So this positive slope is nothing but height upon width. So height is E1, magnitude of E1 है ना, ये mod of E1, because this is negative. Mod of E1 upon width is 1 is equal to slope Q upon epsilon into Nd. And this height is mod of E2, magnitude लूंगा ना, जितनी ये distance होगी, तो mod of E2, E2 तो negative है, mod of E2 upon this distance width is 2 micrometer is equal to also Q upon epsilon into Nd. यही तो होता है. Slope of a line, height upon width, this height is mod of E2. मुझे magnitude लेना इस height का और ये upon width. So you can clearly say that mod of E2 is 2 times Q upon epsilon into Nd, while mod of E1 is Q upon epsilon into Nd. So definitely mod of E2 is 2 times mod of E1. So which option is correct? Mod of E2 is greater than mod of E1. Okay. So move to the next question. This question is very, very beautifully framed, and this is very, very special question. Try to solve this question, and I will make you learn something very beautiful from this question. Very beautifully framed question. Very easy question, but many students will not able to solve it in the examination because of some misconception. If they will be able to solve it, then they will solve it in a complex manner. But you will going to learn something that will make this question very, very easy, or this type of questions very, very easy. Okay. Try to solve it. Okay. Do it fast. Do it fast. Do it fast. Do it fast. Do it fast, 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 fast. Okay. Anybody is getting the question? जल्दी से बताइए आंसर। चलो मैं कुछ सिखाता हूँ। In a PN junction diode at equilibrium, the width of depletion region on N side and P side is given as. At equilibrium, when there is no bias applied, 1.2 micrometer and XP is 2.4 micrometer. When at equilibrium, that is no bias is applied. When we apply a reverse bias voltage of VR volt, then width on N side increased by 0.8 micrometer. So delta XN increase in the width, because when we apply reverse bias, depletion region width increases. It increases on N side as well as on P side. So overall width of depletion region increases. So increase in the width of on N side is equal to 0.8 micrometer. ठीक है, ये दे दिया. Then the junction capacitance per unit area in a nanofarad per centimeter square at applied VR voltage will be, okay, will be. Now remember one formula. We always know that the penetration of depletion region is with respect to doping. Where doping is high, the penetration will be lesser, and where doping will be less, penetration will be high. So Xn upon Xp will be, so penetration Xn, depletion region on N side, will be inversely proportional to doping concentration on N side Nd. If Nd is high, Xn will be less. If Nd is low, Xn will be high. Similarly, Xp. So this relation is Xn upon Xp is equal to Na upon Nd. So if Xn is on the upper side, this corresponds to N side. So doping concentration on N side will be on the denominator side. If Xp is on the denominator side, Na will be on the numerator side. Okay. This is the formula. So penetration will be more on P side. So doping concentration will be lesser on P side. So I can definitely say that Na is less than Nd. Definitely, I can say that. And from this, I can find out Nd is equal to 2 Na. Because Xn is 1.2, Xp is 2.4. So this is 1 by 2 and Nd is equal to 2 Na. So Nd is, the doping on N side is 2 times the doping concentration on P side. Nd is equal to 2 Na. So therefore, penetration on N side is lesser compared to penetration on P side. Now, when we apply a reverse bias, penetration on N side as well as P side increases, so that the overall depletion region width increases. Now, I need to find out the capacitance per unit area at applied reverse bias voltage VR. So if at applied reverse bias voltage VR, the depletion region width, total depletion region width is WR, then the overall capacitance Cj will be epsilon A upon WR. But I need to find out the capacitance per unit area, so divide Cj by A. This is the capacitance per unit area, and that will be equal to epsilon by WR. Epsilon is given, epsilon 0 into epsilon R, and if I can find out the value of WR, then I can find out the value of Cj upon A in nanofarad per centimeter square. Okay, so I need to find out this WR. So WR will be what? Total Xn dash, Xn plus delta Xn. Total अगर XP dash पता चल जाए, XP plus delta XP, then I can find out Xn dash plus XP dash is equal to total WR. Because now Xn dash is what? New width on N side of the region is initial width plus increase in width, that is 2 micrometer. Always remember Xn upon Xp, which is equilibrium depletion region width on N side and P side. This ratio will always maintained in case of increase in width on N side upon increase in width on P side. When you apply a reverse bias, then width increases on N side is delta Xn, width increases on P side is delta Xp. Then delta Xn and delta X will also be in the same ratio. That depends on the doping concentration ratio. So this delta X and delta Xp will also follow this rule of doping concentration ratio, and overall width Xn dash, which is equal to the xn plus delta xn on overall width xp dash will also follow this doping ratio profile. So now I can find out delta xn given is delta xp is equal to, this is nothing but 1 by 2 initial xn xp है ना, this is 1 by 2 है ना. So delta xp will be equal to 2 times delta xn, which is 1.6 micrometer. Okay, so now delta xp 1.6 micrometer. Now xp dash is equal to what? 4 micrometer. Now again you can say that xn dash upon xp dash is 1 by 2, 2 micrometer upon 4 micrometer. And total depletion region width at reverse bias VR voltage is xn dash plus xp dash is equal to 6 micrometer. Put this value here in centimeter, because you need to find out per centimeter square, and this epsilon is already 8.85 into 10 to the power minus 14 farad per centimeter is already given in farad per centimeter, and then convert into farad will be converted into nanofarad by using 10 ki power minus 9, and then you can find out the solution whatever it comes to. Okay, so I am not calculating, you can calculate it further. So try to solve this question. This is also a very beautiful question. Try to solve this question. Okay, try to solve this question. Try to solve this question, bachcho. (177). I haven't considered increase in p side, so your answer is wrong, beta. Your answer is wrong. Whatever the answer is, you can find it. New depletion width you need to find out at the applied reverse bias voltage of VR voltage, because width will increase. Increase on n side is delta xn. Increase on p side is not given, because you can use the information given earlier to find out the increase in the width on p side. So maintaining same ratio as xp is 2 times xn, delta xp will also be 2 times delta xn, and xp dash will also be 2 times xn. So that ratio will always be maintained, because that ratio is nothing but depends on the ratio of doping concentration. Increase on the depletion region width on n side and p side follow the same ratio. Total depletion region width on n side and p side, they also follow the same ratio, and width at equilibrium on n side and p side, they also follow the same ratio, Na by Nd or Nd by Na. Okay, solve this question. Anybody got the answer? Anybody got the answer? Please tell me the answer. Please tell me the answer. This is from BJT. This is from BJT. This is from BJT. In a PNP transistor, emitter and collector currents are given as I is equal to 1.2 milliampere, IC is equal to 1.18 milliampere. Reverse saturation current of collector base junction ICO या I naught is given as 5 microampere. Then the value of base current. यहाँ पे many of you can confuse by this value I naught. Whenever you are given with emitter current or collector current, they are always the terminal currents. Current that flows from the emitter terminal is called as emitter current. Current that flows from the collector terminal is called as collector current. Current that flows from the base terminal is called as base current. Whether the BJT is in ideal condition or non-ideal, because here reverse saturation current is non-zero. This is non-ideal case, and that's why you can confuse. But the emitter and base and collector currents are terminal currents, always mentioned as terminal currents. IB is current that is flowing from the base terminal. Whether BJT is operating in ideal condition with I naught 0 or I naught is non-zero. So in every formula you have read, IB, I and IC are always terminal currents, whether BJT is operating as ideally or operating as non-ideally. Okay. So, and because there are three terminals, current entering from base, since this is PNP transistor, so current is entering from emitter is I. There are two more terminals and it is exiting from collector terminal as IC and exiting from base terminal as IB. So this is entering current and this is incoming current, and these two are outgoing current. So KCL will always hold good and I can always write I is equal to IB plus IC. This equation will never fail, whether BJT is operating in ideal condition or non-ideal. Here non-ideally, but this equation always holds good. So base current IB will be I minus IC, and I is given as 1.2 milliampere minus IC is given as 1.18 milliampere. So answer will be 0.02 milliampere. So this is IB. Now when we calculate the current gain of any BJT, then effect of this non-ideal current will be neglected, and then to neglect the effect of this non-ideal current, when we derive the formula, then we come up with the formula IC is equal to IB plus beta IB plus beta plus 1 ICO. Here also IB is the terminal current, IC is the terminal current. This is not like ki this is current of ideal case, this is current of non-ideal. Whatever current is flowing from collector is IC, whatever current is flowing from base is IB. And when ICO is non-zero, then this formula is derived. When ICO is 0, IC is equal to beta IB formula is valid. So from here beta is nothing but IC minus ICO. How this formula is derived, when I will teach EDC in paid batches, then I will explain how this formula comes very carefully. IC minus ICO upon IB plus ICO, and IC minus ICO, IC is 1.2 microampere, convert it into microampere. 1.18 is nothing but 1180 microampere minus 5 microampere divided by IB is 0.02 multiplied by 1000, 20 microampere plus 5. This comes out to be 1175 divided by 25, and this comes out to be 25 चौक के 100 नहीं 25 47. So beta will come out to be 47. Not like ki IC upon IB. IC is 1.18 upon 0.02, and that then it comes out to be 59. Wrong. 59 is wrong. If ICO is 0, then current gain will come out to be 59, and if ICO is non-zero, current gain will come out to be 47. So always remember IB, IC, I, whenever they are given or whenever they are used in any formula, they are always terminal currents, whether BJT is in ideal case or in non-ideal case. Okay. So this is a question of mass capacitor. Try to solve it. Very beautifully framed question, and you will going to learn something from this question. Okay. Try to solve this question. चलिए सॉल्व करिए जल्दी से इसका आंसर. First you need to find out the type of MOSFET, then you will be able to relate it. Okay, then you will be able to relate. High frequency CV characteristic. Always remember, in case of high frequency CV characteristic, the highest capacitance value is always in accumulation region. So this is accumulation region where you are finding out the highest capacitance value, and this capacitance is always equal to the capacitance due to oxide layer, EOX A upon TOX. Okay. And in case of high frequency, CV characteristic, the lowest capacitance value, which is constant at lowest value, is always in case of inversion mode of operation. So this is inversion mode of operation, this is accumulation, and when we are moving from accumulation to inversion, capacitance falls, capacitance decreases. Why? Because in depletion mode of operation, as we increase the voltage on negative side or positive side, in case of N type of MOSFET where substrate is of P type, when we increase the voltage above 0, then capacitance falls and we are in the depletion mode. And in case of P type MOSFET where substrate is of N type, when we decrease voltage below 0, then depletion mode starts, and as depletion mode starts, depletion region width increases, and as depletion region width increases, there is another capacitance added in series with the oxide layer capacitance, and that capacitance is due to depletion region, and as depletion region width increases, capacitance value decreases, and in series combination with EOX, overall capacitance decreases, that is mass capacitance decreases. And when we reach this at this point, this is the common point of depletion mode and inversion mode, and from there onwards inversion mode operation starts. Okay. So at this point the capacitance value is minimum, and at this point the thickness of depletion region is maximum, and capacitance due to depletion region or depletion thickness is the minimum, at the minimum value, and that depletion region minimum capacitance in series with the oxide layer capacitance causes the overall capacitance at the minimum value. Okay, so I can say that this is C max, which is equal to 9 microfarad, and it is nothing but equal to COX, that is nothing but EOX upon TOX into A. Okay, first, and this is C min, minimum value of, okay, and this is nothing but COX in series with the minimum capacitance value due to depletion region, and minimum capacitance value due to depletion is nothing but due to the maximum depletion region thickness. Okay, so C dep min, when depletion region capacitance is minimum, then series combination of COX and C depletion will be at minimum value C min. Okay, so COX plus C dep min. So from here I can find out the value of C dep min, because C min is given as 1.5. 1.5 is equal to COX is nothing but 9 microfarad. So 9 C dep min is equal to 9 plus C dep min. Okay, so here 1.5, 9, 7.5, 7.5 C dep min is equal to 9 into 1.5. So C dep min is equal to, it comes out to be 9 into 1.5, 9 upon 5 हो जाएगा, 9 upon 7.5 into 1.5. This is 5, this comes out to be 1.8 microfarad. So the minimum value of depletion region capacitance is nothing but 1.8 microfarad, and this is belongs to epsilon Si, because let us assume that the semiconductor is of silicon, the substrate is of silicon. So epsilon Si या epsilon Sc लिख देते हैं, semiconductor जो भी हो, है ना, into area of cross section A upon the maximum width of the depletion region W max. epsilon Sc A upon W max, हमें इसकी वैल्यू पता चल गई, because minimum capacitance depletion region capacitance corresponds to the maximum depletion region thickness W max. Now what is asked in the question, let us try to find out that value. If doping concentration in substrate is Ns, and substrate is which type? In P type MOSFET substrate is of N type, so this Ns is nothing but Nd, Ns is equal to Nd. So 2 into 10 to the power 15. and the area of cross section is A equal to 0.9 centimeter square. Then the value of maximum electric field when depletion region has maximum width inside substrate. So inside the depletion region, at the junction capacitance value will be maximum. Just like in the case of PN junction diode, inside depletion region at the junction electric field is maximum, and the maximum value of the electric field is given by E naught is nothing but Q upon epsilon into ND into depletion region width on N side, depletion region width on N side, and this is also equal to Q upon epsilon into Na into XP, where Na is the doping concentration on P side and XP is the depletion region width on P side. But here only one type of substrate is there, only N type of substrate is there, and there is depletion region width whose width is Xn. Then the only formula that can be used for finding out the maximum electric field is Q upon epsilon ND into Xn. If substrate is of P type, then this formula will be Q upon epsilon Na into Xp, where Xn is the width inside depletion region, and this depletion region is nothing but inside the substrate, and that depletion region width is nothing but W max inside the substrate. Depletion region, where the depletion region is inside the substrate, and substrate is of N type. So this Xn is depletion region width on N side, that is nothing but in substrate, and in substrate region the width of depletion is in W max. So I can say that this E naught is nothing but Q upon epsilon ND into W max. This Xn is the total width on N side, and that total width on N side is W max, because they are saying that the find out the maximum electric field when depletion region has maximum width inside substrate. Means when depletion region width is maximum inside substrate, means this Xn is equal to W max. This is width on N side of the region or N type substrate in case of MOSFET. Now here the value of epsilon is not given. This epsilon is basically of the semiconductor, obviously, because this depletion region in the substrate region or in the semiconductor region. But this epsilon 0, epsilon r is not given in the question. So from where I can find out this value? Look it very carefully. Look it very carefully. Epsilon SC upon W max can be find out by 1.8 microfarad divided by A. And here ESC, W max upon ESC. So W max upon ESC can be find out from here. ESC is equal to A upon 1.8 microfarad. And put this value here. Q into ND into what? W max upon ESC is A upon 1.8 microfarad. Convert it into farad. Q is ND is known, A is known, Q is known, 1.8 microfarad. Everything is known. You can find out the value in volt per centimeter. So Q will be in coulomb, ND will be in per centimeter cube, A will be in centimeter square, so per centimeter will remain, and this will be 1.8 into 10 to the power minus 6 farad. Q upon farad, Q upon C will be volt. Q is equal to CV, है ना? Q is equal to CV होता है, तो Q by C is equal to volt होगा. तो Q upon C, Q coulomb में, C farad में, स्टैंडर्ड यूनिट, तो Q upon C will be in volt, and volt आ जाएगा और ND into A से पर सेंटीमीटर आ जाएगा. So answer will be volt per centimeter. So from here you can find out the answer. Okay, I'm not solving the whole question. Just put the value of Q ND per centimeter cube in per centimeter square, Q in coulomb, and this 1.8 into 10 to the power minus 6 farad, and you will be getting the right answer. Okay, so we'll move to this question. We'll move to this question, whatever the value is. Okay, first note down this question, and then in the next slide you will be getting the option. You will be getting the option. An N-type enhancement MOSFET is biased as shown below. The graph between transconductance GM and the voltage VSS. This voltage is minus plus, and this is a variable voltage. Okay, this end is at higher potential, this end at lower potential. This VSS voltage is varying and this applied voltage is VDD. Okay, so when this voltage is varying VSS, then how the transconductance of this MOSFET will change? The plot between GM and this VSS will be, this value is VSS, this is nothing but VSS, and this is nothing but VDD. Okay, okay. So you need to find out the graph between GM and this VSS. When VSS is varying from 0 to infinity, what will be the graph between transconductance of this MOSFET and this VSS voltage? You need to find out the graph, and these graphs are given. This is VTH, basically VTH. This is x एक्सिस पे VSS है, ठीक है ना, और ये y एक्सिस पे GM है. Similarly, this is VTH, this is VSS, this is GM, this is VTH है ना, ये थ्रेशोल्ड वोल्टेज है VTH. लीनियर फिर नॉन लीनियर, ये VDD माइनस VTH वाला पॉइंट है. दिस x एक्सिस इज VSS एक्सिस एंड दिस इज GM. This is non-linear from VTH to VDD minus VTH, then this is linear VDD minus VTH to VSS further onwards. So you need to find out the graph between GM and VSS. These 4 graphs are given. These 4 graphs are given. Try to find out the answer. Okay. Try to find out as quickly as possible. Okay. जल्दी से solve करिए. क्वेश्चन पे आ जाते हैं, ठीक है. आप ग्राफ इसी क्वेश्चन से देख के प्लॉट करिए, 4 ऑप्शन में से कोई तो आ ही जाएगा, ठीक है. एन एन टाइप इनहेंसमेंट मॉसफेट, तो ऑलवेज रिमेंबर फॉर एन टाइप इनहेंसमेंट मॉसफेट थ्रेशोल्ड वोल्टेज VTH विल ऑलवेज बी पॉजिटिव, एंड फॉर डिप्लीशन टाइप ऑफ एन टाइप मॉसफेट द थ्रेशोल्ड वोल्टेज इज नेगेटिव. सो पॉजिटिव थ्रेशोल्ड वोल्टेज है इसका. द ग्राफ बिटवीन ट्रांसकंडक्टेंस GM एंड वोल्टेज. ट्रांसकंडक्टेंस GM होता क्या है? व्हाट इज द ट्रांसकंडक्टेंस? Transconductance GM is delta IDS upon delta VGS at constant VDS. So when the transconductance formula will be applicable? When there is current in the MOSFET. What is the rate of change of current IDS with respect to voltage VGS at constant VDS? That is called as the transconductance GM. So you need to turn on the MOSFET in order to have a valid value of transconductance GM. If your MOSFET is in off condition, then transconductance will definitely be 0 because the current is 0. So first the MOSFET should be on, and if MOSFET is on and operating in triode region, because when MOSFET is on, it can be in triode region, it can be in saturation region. Okay, so if MOSFET is on and in triode region, then transconductance formula is 2Kn into VDS, and when MOSFET is on and in saturation region, then the transconductance formula is 2Kn VGS minus VTH. Okay. So first I need to understand whether my MOSFET is on or off, and if on, in which region it is operating. If it is operating in triode region, then I will use this formula to find out the transconductance value. And if it is operating in saturation region, then I will use this formula to find out the transconductance value. Definitely. Okay. Now, first I will try to find out whether my MOSFET is in on condition or off condition. Okay. Let me try to find out. So for that, I need to find out the VGS value. This is source VS. This is source VS. This is source terminal, not this. Always remember. The current is outward directed, that means this is N-type MOSFET, and from where the current is outward directed, that terminal is nothing but the source terminal, and opposite to that there is drain terminal D, and this is gate terminal VG. So to find out whether my MOSFET is in on condition or off, I need to find out the VGS value. If VGS is greater than VTH, MOSFET is in on condition. If it is less than VTH, that is in off condition. Okay, so let me try to find out that value. If this voltage is Vs, then this minus plus, this voltage will be what? This is a battery of potential VSS, and minus is at Vs, then plus end will be at VSS plus Vs, so that the potential difference is V plus minus V minus VSS plus Vs minus Vs is equal to VSS. So plus node of the battery is at VSS plus Vs, minus node is at Vs, and the potential difference is VSS. and this node is connected to gate. So VG is at which potential? VSS plus source node potential Vs. So VG minus Vs is what? VG minus Vs. This is nothing but VGS is equal to kya? VSS. So VGS is nothing but equal to VSS voltage. And if VGS is greater than VTS, then my MOSFET is in on condition. And if VGS is less than VTS, then my MOSFET is in off condition. So if VGS is less than VTS and VGS is nothing but equal to VSS, if VSS is less than VTS, then definitely VGS will be less than VTS and my MOSFET will be what? Off. And when MOSFET is off, current is 0, transconductance is 0. So for VSS less than VTH, my transconductance will come out to be 0. So in whatever graph, if for VSS less than VTH, GM is non-zero, that graph will be wrong graph. Because for VSS less than VTH, my MOSFET is off and GM should be 0. And for VGS greater than VTH, that is VGS is equal to VSS. If VSS is greater than VTH, then VGS is equal to VSS, then VSS will definitely be greater than VTH. Then my MOSFET is in on condition. If VSS is greater than VTH, VGS is equal to VSS, then VGS will also be greater than VTH, and then my MOSFET will be on. And if my MOSFET is on, then I can use this formula for transconductance or this, depending in which region my MOSFET is operating. So first I need to find out the region of operation, and for that I need to find out the VDS value and VGS value. What is VDS value? See clearly, VD is at VDD. VD minus VS is VDS. VD is at VDD. VDD is at high potential, 5 volt, 10 volt. VDD minus VS. VS is nothing but, okay, VS is at VS. VS is at VS. And VGS minus VTH is what? VGS minus VTH is what? VGS is nothing but at equal to, okay, let me now try to find out this value. This is very, very interesting. This is very, very interesting. Okay, let me come to VD is at VDD and VS is at what voltage? This battery is minus plus VSS volt battery. Okay, and the plus node of the battery is at 0 volt. Then minus node of the battery will be at minus VSS volt. So that 0 minus VSS will be equal to the potential difference of VSS. This battery has a potential of VSS volt. Plus to minus potential difference is VSS volt. And plus node of the battery, you can clearly say that the plus node of the battery is connected to ground. So plus node is at 0 potential. So minus node means this node will be connected at minus VSS potential, so that the potential difference is 0 minus VSS is equal to plus VSS. So VS is nothing but minus VSS. So I can put the value of VS at as minus VSS. So it will come out to be VDD plus VSS. And VGS minus VTH will be equal to, because for finding out the region of operation, I need to compare VDS and VGS minus VTH. And VGS minus VTH is nothing but VGS is equal to what? VSS and minus VTH. So I can clearly say that VDS will always be greater than VGS minus VTH. Why? Because VDS is what? VDS is nothing but VSS plus something. VDD will always be a positive voltage. So I am adding something in VSS, then I am getting VDS value, VSS plus something. While in case of VGS minus VTH, I am subtracting something out of VSS. So VSS minus VTH will definitely be less than VDD minus VSS. Whatever the value is VSS is, you are adding something to VSS and then getting VDS. And here you are subtracting something out of VSS. So this value is less than VSS. This value is VGS minus VTH is definitely less than VSS. Because you are subtracting something out of VSS, and this VTH is positive value. So you are subtracting something from VSS, then this VGS minus VTH will definitely be less than VSS. And here you are adding something to VSS plus VDD, and this VDD is also positive. So this value is always greater than VSS. So since this value is greater than VSS and this value is less than VSS, definitely VDS will always be greater than VGS minus VTH in this configuration. So this VDS is always greater than VGS minus VTH. That means this MOSFET is always operating in saturation region, and I can use this formula always for finding out the transconductance value GM. So GM is equal to nothing but 2Kn. Kn is constant. VGS value is VSS minus what? VTH. Threshold voltage, a constant value. Kn is constant value. GM is depending on VSS to the power 1. And whenever something is depending on power 1, then that variation is nothing but linear variation. This is y and this is m and this is x. Y is equal to m into x plus c. This is a linear line equation with a slope of 2Kn. So for VSS greater than VTH, transconductance is varying linearly with VSS with a slope of 2Kn, and for VSS less than VTH, MOSFET is off and transconductance is 0, and that is where this is absolutely right answer. From 0 to VTH, VSS is less than VTH and MOSFET is off and transconductance is 0, and when VSS is greater than VTH, then VGS is greater than VTH and MOSFET is on, and when MOSFET turns on, it enters into saturation region because VDS is greater than VGS minus VTH, and transconductance value comes out to be 2Kn VSS minus VTH, which is a linear relation, and slope of this line is nothing but 2Kn. Y is equal to mx plus c. So this variation is absolutely correct and A option is absolutely right. So this is the last question. This is the last question of this series. Okay. This is the last question of this series. Try to solve this question and find out the answer. Okay. Try to solve this question and find out the answer. So whenever the previous question is just to make you understand that whenever you are going to find out the transconductance value in case of MOSFET, always first find out the region of operation of the MOSFET, because there are two formulas of transconductance depending on the region of operation. If it is operating in triode region, then formula is 2Kn VDS, and if it is operating in saturation region, then formula is 2Kn VGS minus VT. So be careful which formula you are using and then conclude the answer. Okay. Try to find out this question. Try to find out the solution of this question basically. Okay. So anybody? Not a very lengthy question. Many datas are given, but question is very tricky and very easy, I can say that. Tricky as well as easy. And these type of questions are constantly asked in GATE examination. You try to find out whether your concepts are crystal clear or not. You are just remembering the formula, you are just mugging up the formula, then you will be able to find out the wrong answer always in GATE examination. For an N-channel MOSFET, following information is given. Threshold voltage VTH is equal to 1.2 volt. Conduction parameter Kn is equal to mu and Cox W by 2L is 1.5 milliampere per volt square. The value of VDS drain to source voltage is changed from initial value of 2 volt to final value of 4 volt at a fixed value of VGS 4 volt. Then fixed value of VGS 4 volt. Initial value of transconductance is found to be GM1 and final value of transconductance is found to be GM2, then the value of ratio of GM1 GM2. So VGS is fixed. What is VGS value is 4 volt. VDS is changed from 2 volt to 4 volt. 2 volt is the initial value and 4 volt is the final. So initial value of VDS is 2 volt. And corresponding to these two values, transconductance is GM1. VGS is fixed at 4 volt, but VDS is changed from the initial value 2 volt to final value 4 volt, and then comes out to the, then trans conductance value comes out to be GM2, and then you need to find out the GM2 by GM1 ratio. Okay. Now, whenever I will be using the formula for trans conductance, I need to find out the region of operation. I always say. Okay. So in first case, in which region MOSFET is operating in? How you can find out? By comparing VDS with VGS minus VTH. If VDS is greater than VGS minus VTH, saturation region. If VDS is less than VGS minus VTH, triode region. So here VGS is 4 volt and VTH is 1.2 volt. VGS minus VTH is 2.8 volt. Okay, 2.8 volt. And VDS is 2 volt. So VDS is less than VGS minus VTH because 2 volt is less than 2.8. So here MOSFET is operating in triode region, and formula for transconductance is 2Kn into VDS, and VDS value is 2 volt. So it comes out to be 4Kn. Okay. When VGS is kept at 4 volt but VDS is increased to 4 volt, then at this values of VGS and VDS, transconductance is GM2. So here the region of operation, then only I will use the formula. VGS minus VTH is still 2.8 volt, but VDS is 4 volt. So this 4 volt is greater than VGS minus VTH 2.8 volt. So here the region of operation is saturation, and transconductance is 2Kn into VGS minus VTH. Okay. So putting the value 2Kn, VGS is 4 volt, VTH is 1.2 volt. So this comes out to be 2 into 2.8 Kn. GM2 upon GM1 क्या आ जाएगा? Kn can cancel. 2 into 2.8 divided by 4. It comes out to be 1.4. Okay. If you directly use the formula 2Kn into VDS here, then you 2Kn into VDS is 4 volt, then this will come out to be 8Kn, and ratio will come out to be 8Kn upon 4Kn. So ratio will come out to be 2. You can think that VDS is double from 2 to 4, and 2Kn into VDS, transconductance is depending upon VDS. Since VDS value is double, transconductance will double. Therefore GM2 upon GM1 will be 2. But here, as VDS is changed from 2 to 4, region of operation changed, and transconductance changed to this value 2Kn into 4 minus 1.2, neither nor 2Kn into VDS. Instead of 2Kn into VDS, the transconductance is 2Kn into VGS minus. So transconductance is 2 into 2.8 Kn. So the ratio is 1.4. Okay, clear? Clear? So always in case of MOSFET, whenever you are going to use the formula of transconductance, always first find out the region of operation, because there are two formulas which is valid. It depends on the region of operation. Okay. Everything is crystal clear. Thank you so much everyone, and hope I made you understand something which are going to be very, very beneficial for the upcoming GATE 2023 examination, because these questions are not the questions which will be directly asked in the GATE examination, but the learning of these questions will definitely be beneficial in upcoming GATE examination for sure. And that's why this series is. Similarly, Super 30 series is going on. This is Super 10 series for English, GATE Wallah English channel, and similarly Super 30 series is going on GATE Wallah English channel, and at 7 PM today, Vishal sir will be live with control system and signal system. So don't miss that session. That is going to be very, very beneficial for your upcoming GATE 2023 examination. You learn many new concepts. Thank you so much, dear. The purpose of session is always to make you learn something beautiful, to make your concepts crystal clear. Always, not the question. Learning of questions is very, very important. So I can end this session. Thank you so much everyone for attending this session. We'll keep doing these sessions for your benefits always. Just be live whenever we are conducting any sessions. Okay. Thank you so much everyone. Take care. जय हिंद।